Okay, well, good afternoon, everyone. It is my pleasure to welcome you to another delivery of the Neocortex seminar series. My name is Paula Buitrago. I'm the principal investigator of the Neocortex project, which is funded by the National Science Foundation and is delivery collaboration with Cerebras Systems and Hewlett-Packard Enterprise. Neocortex is hosted at the Pittsburgh Supercomputing Center, which is a joint effort between Carnegie Mellon University and the University of Pittsburgh. And I have to say, it is my absolute pleasure to introduce Jessica, who will be delivering a talk titled Physics-Aware AI at Scale, Neural Compression and Vision Transformers for Simulation Data. And Jessica is a PhD student, candidate at Carnegie Mellon University. And she has been using Neocortex for a period of time. She also participated recently in a cyber training program that we delivered in the summer that is called ByteBoost. You are all invited to consider applying for ByteBoost. Maybe Jessica can share some thoughts on that as well if it's not already part of the presentation. And she has just been great to work with. Part of her project in ByteBoost resulted in a scientific paper being published in the Supercomputing Conference, which is the top conference in our field in advanced computing and scientific computing. So with that, I'll allow Jessica to just take the stage. Yeah?
All right. Yeah.
Okay, go ahead, Jessica. Let's
show my screen.
I'm gonna stop sharing.
Okay. All right. So thanks, Paula, for the great introduction. Like she mentioned, today I'm going to be presenting a little bit of the work that I've done on physics-aware AI at scale, is what I'm calling it. A lot of the work that's going to be presented here have solely been used using Cerebras via the Neocortex system at Pittsburgh Supercomputing Center. So also happy to take questions about that if anyone has them. So right now, we're going to be talking about both neural compression and vision transformers for simulation data. A little bit about me. I am a PhD candidate, third year, end of third year at Carnegie Mellon University. And it's good to contextualize because where I live in the simulations, because simulation means different things to different people. I live in the mechanical engineering department. So where simulation works for me is within the engineering design process. So this process has different representations. I like to think about it as going from functional requirements all the way to manufacturing requirements. So if a customer comes in trying to design something, they would give us some sort of description of what they want to design. Engineers go through that process of translating it to something that can be tested for and measured, called functional requirements. And through a number of steps, you go through getting to the actual manufacturing requirements, and then that gets passed off to actually manufacturing this thing. Where simulation lives for me is in the engineering validation phase, where prior to physical manufacturing, you're able to validate if the initial customer requirements or the functional requirements can, or the functional requirements do meet the customer requirements. So there's a lot of benefits for engineering validation. It's not as expensive to build something and then test it out in the real world. You can do similar evaluations relatively cheaper. If you think about things like planes and cars that need physical validation, if you do an initial validation for that in simulation, it's necessarily cheaper. But there are also some challenges with engineering validation, and I'm going to focus on one of them in this presentation. My PhD focuses on a bunch of them, but I think today is pretty nice to talk on a problem that I don't think is mentioned too much in the field, especially as it relates to scientific machine learning. This has come up recently. It's called a bunch of different things: AI for discovery, AI for science, science ML, scientific ML. It's all around the same idea of how can we use ML and combine it with these scientific processes that we've developed over a millennia to be able to understand how we simulate and complex systems. So can we use these simulations to recreate and create an automated workflow or pipeline to be able to explain what the simulations are showing, or even go beyond that to be able to discover new parts of the simulation that wouldn't have previously been discovered just due to the nature of the volumes of the simulations that are being run. And it's really huge field. It's recently developing, but I think one issue right now that's currently plaguing scientific ML that necessarily hasn't plagued traditional ML paradigms, if you think about things like large language models, is physics-based simulations take up a lot of data. So these are some of the simulations out of a professor's group at Johns Hopkins, Dr. Mittal, and what we're looking at here is cardiovascular simulations of blood pumping through a heart or aorta in this case, simulations of insect swarms. I believe that's a butterfly. And this simulation, which I love, which is a person doing a dolphin kick. So it's not, I didn't see it at first, but once you know that, it's actually pretty obvious. These simulations take up a lot of data because you're tracking at each point in time. Each of these meshes or these nodes have to be tracked from t=1 to t= however long you're running the simulations. So you need to be able to keep track of things in the case of fluid dynamics, like velocity, of pressure, of different densities. Those kind of dimensions or features of data to be tracked with every given time point over every given mesh resolution, so that explodes pretty quickly. And that's just for one simulation. So you can see a situation where you can get to a point where you're learning multiple, if you want to train a model like you would do with traditional ML, where scrape the internet, train this model, get it to predict something. If one data point is a petabyte of data, you can't really train a lot of data because we don't have that current memory to be able to store millions of petabytes of data to get reasonable AI models. So I think some research labs have been doing some work in this field to be able to democratize access to well-structured data that's reasonably ingestible for training purposes for scientific ML. One of them is the WELL, which is the data set that I'm going to be focusing on in this presentation. This data set is still about 15 terabytes of data, so it is still very large, but it's largely manageable than the petabytes of data we saw in the previous slide. So there's this idea of how can we go and use this data in a way that we can use for scientific ML processes. For that, I'd like to introduce two paradigms, and these are the two different research that are going to be presented on this presentation. So the first is the work that Paula alluded to, which is the work we did out of ByteBoost, which is going, instead of trying to learn raw data of this simulation, which can be large, simulations have an inherent reduced representation just by nature of humans not being able to read through raw data. A lot of really interesting UX and visualization engineers have created simulation video, simulation images, simulation displays and interfaces as a reduced representation over that. So the idea of learning over reduced representations is, can we learn skipping all the raw data, just learn over the images and the videos themselves? And can we use that to train models? So that's where the vision transformer comes in that I'm going to be speaking about. And then the second paradigm is, okay, maybe there's some data that we can't necessarily abstract away from just images. And if we want to use the raw simulation data, is there a way we can take it and compress it into a reduced representation? Then that can be used in these kind of machine learning paradigms. So there's a lot of ways of doing that. The way that I'm going to present is the implicit neural compression. That work actually recently got accepted for advanced scientific computing this year. So Still pretty new, but hopefully it's interesting enough for this audience. So I'd like to start with the first part, which is learning over reduced representation. And this idea is not necessarily new. A lot of different contexts have used reduced representations to learn over data that might be necessarily too large to learn in different contexts. So for example, this paper trained a multimodal autoregressive model. They were dealing with audio data, but instead of using raw audio data, which could be megabytes and megabytes of data, they took the audio profile and transformed it into something called a spectrogram, which is what you're looking at on the screen. And this is a reduced representation because this is the image that we're looking at. And they used this spectrogram to train an audio vision encoder using the VIT, so vision transformer. So this way you moved away from the raw audio files, and now you're looking at the images for the audio via the spectrogram. So it's not anything new. We're going to be looking at this vision transformer. The thing that is new is how it's being applied to physics simulation, which has different considerations than using traditional vision-based vision transformers. So if you are aware, there are some pretty common ones out there. One of them is CLIP and the other is DINOv2. I believe DINO is out of Meta or V3. And these models are a general representation. If you take enough images and you train this vision transformers, you're able to learn cross-domain analysis. So for example, this picture, guacamole here, you can be able to tell it apart just by sheer volume of training, multiple different types of samples, multiple different types of image augmentations, and using that to predict what this photo is. DINOv3 has also been used for medical image like segmentations, like segmenting healthy cells from non-healthy cells. So we see on a general basis and more specific basis that these models have been applied. So the question was, how can we actually use this technology that has been used for traditional everyday images to medical images to apply to physics-based simulations? And that was a question that we wanted to answer during the Byte Boost conference, is training something called a physics-aware vision transformer. We have all this data that we've gotten from the well. Can we use it to train a vision transformer that's able to understand what's going on physically in the simulation? So the process in which we did that is taking raw simulation trajectories, which you can see over here. So this is on an image basis where we have the time steps associated with each of these images. Goes through a bunch of pre-processing physics-aware steps that I'm going to be explaining in the next couple of slides. And then through the standard vision transformer, the standard architecture that DINOv2 at that time, I believe, used, using that same transformer, training from scratch, can we actually beat out DINO and CLIP using things like domain classification, predicting the next time step, and actually looking at what this embedding space is for the vision transformer. So that was the idea. Like I mentioned, we can't do certain things that you would traditionally do with everyday images when it comes to simulation images. One of them was cropping. So it's very well known to have something called like random crops and rotations when you're thinking about training traditional CNNs, traditional vision transformers, where you want to take an image and get it at a point where it's able to be processed. You don't want a situation where you have different image sizes. There are some augmentations you can do from getting it to the same size, but it creates a well-behaved model if you can standardize as much as you can. But we want to keep physics informed, right? We can't just randomly crop these images because that's where our data is being embedded in these images. So cropping was done using a center expansion technique where we don't distort the original image, rather we pad it so that we have a uniform image across different types of simulations with different types of dimensions. The other thing that's more specific to physics-aware is color augmentation. This is something that is also done with random images, but in this case, we have these kind of templates that have been traditionally used for simulation. So there's different types of simulation gradients and color schemes like radius and black and white and inferno and plasma. And this is cool, warm, that is very traditional for simulations. We don't want a simulation to just learn that cool, warm is always this type of simulation. So that's something that we also wanted to play around with, in addition to just creating a black and white image, so that that's not an implicit factor that's learned within the model weights. The other thing is random augmentation. So we can't take an image and then just randomly flip it or rotate it. That wouldn't make much sense physically. So we have to think about something different. The thing is, since these are videos, we already know what the time step projection is for each of these images. So given time equals 0, time equals 1, we can train the model to say at this time equals 50. This is an augmentation of this initial image. So that way it's trying to learn some of the temporal aspects of the simulation while still behaving or keeping under control the underlying physics so that it's not something that doesn't make sense, like a random rotate or flip. So these are just things that I wanted to point out that were a little bit different. Other than that, the traditional techniques for training a vision and transformer is the same. You go through an embedding process where you break up a bunch of images into patches that goes through multiple layers of the transformer to do some sort of end task or downstream tasks. Today, I'm going to be presenting results on 2 of those downstream tasks. One of them is the classification of simulations. We saw different types of simulations in the well dataset before. Is it able to recognize based on this image, which bucket does it belong to? And then the more difficult task is it able to predict based on the initial image that it's given, what the next time step of the image would be. So this is something that requires understanding of that temporal component. And then just visualizing what the actual dimension is using a PCA or principal component analysis diagram and a TSNE plot that just tries to see how well or how different the models are learning based on the weights of the network. So there we go. These are some of the results from that work. The vision transformer that was trained using that 1 week of ByteBoost was able to achieve pretty competitive classification performance. So this is which bucket does it belong to. You can kind of see the first column here is the vision transformer we trained based on the raw data from the well dataset. And then the same kind of embedding space from both DINO and CLIP. DINO and CLIP are very, very similar in terms of what's being learned in the embedding space, and we see a completely different type of learned embedding space from the physics vision transformer, from both the TSNE and the PCA plots. We also wanted to predict this accuracy comes from the classification that we talked about. So which bucket does it belong to? DINO and CLIP, being very big models, are really good at that. But the same thing for the vision transformer we trained is also very high in terms of the accuracy. Where the models struggle the most, which is that more difficult task that I talked about, which is given this image, can you predict what the next time step t=2 would look like? All 3 models struggle with this, but what we're seeing with the physics transformer that we trained is that it's higher than the large DINO and the CLIP-based models for things like the coefficient of determination, the mean squared error, and the silhouette score here is reflecting the differences between these embedding plots. So that's something that shows how well separated of those classes. We're starting to see some sort of improvement, but what's really great about this work is that based on the speed up that we get from the Neocortex Cerebras system is we're able to train this embedding space in hours rather than in days. So these kind of dino CLIP models reported on A100 days and weeks to train. This is something that can be trained in a day. So in order to kind of augment, test different things, these are something that can be easily and scalably done rather than trying to burn a lot of compute training these large models. So that's kind of the first work where we're trying to answer, do we even need these raw simulation data? Can we take the compressed representation as an image and use that to learn physics? We saw some limitations with that. So there's a need to go beyond images and go back to the simulation data that we're trying to learn. And this is the second work that I'm going to be presenting, which goes into more of the neural compression-based workflow. So actually, before I get into this, I'll probably just explain what neural compression is. Those who are not familiar with it, but it's or implicit neural compression, which is any sort of like implicit learning is the idea that if you have a neural network, it's associated with nodes which account for weights and biases of the neural network architecture. And if you give it an input, it maps to the output via these weights and biases. So the numbers associated with each of those nodes of the neural architecture. So the implicit representation is we learned these weights already. Can we use this neural network weights and biases, those numbers that we've learned, giving a new input to get the output, which is good. That's what we traditionally do. But a lot of people, like I showed in the previous step, just use this for downstream tasks. The actual weights of the model are not necessarily focused on. But these weights are really good because depending on how big you make your model, that's the model of the neural network, you're able to store a lot of information with these weights that don't necessarily require a lot of space. So these are on the order of megabytes, just those matrices from the weights and the biases versus the tons of data that comes out of simulation. So people have been looking into neural compression, where given an input and an output of the data, can we train this long enough and get high enough accuracy and then focus on the neural weights as our function that given a new state of input data, pressure and velocity is able to return things that we're interested in. So this field is something called lossy compression. It's not necessarily new, like we saw in the previous slide, there's really nothing new. A lot of previous works have been using this, from Shannon's entropy, which is the equation that we're looking at here, just the idea that this is the lower limit of things that you want to be able to represent. You can't really compress past this. So traditional compression will use something called lossless compression, where you don't lose any data. If you give it the same inputs, it's going to get the same outputs. But that has its limitations in how much it can compress. If you want really large compressions, which we need for a lot of these simulations, you need something called lossy compression, which is the semantic neural compression technique here, as well as others. So the paper that I'm showing here in this slide for semantic neural compression is out of the medical domain as well. It learned this kind of input-output mapping space, but as applied to medical images, the medical slides are multidimensional. There's multiple things in them that you want to track. They can be really big because they have really high resolutions to be able to zoom into a specific spot. So there was this idea of patchifying it, training neural compression, and being able to return an image based on the next image that you put into the system. So it's not new, but again, we're taking this technique and we're going to be applying it to traditional or the simulation data that we've been looking at. There's two sort of challenges with that approach. Like I mentioned, lossy means you might lose some things. And the biggest thing here is you don't want to lose important physics phenomenon. And we're going to this is actually some of the results that we saw. And I'll be talking through this later in the presentation. but you want to be able to preserve, especially critical areas of simulation points. That's not something that you want to lose within this compression and uncompression process. That is the implicit neural network. But the whole idea is that you're able to learn a continuous implicit function. So your implicit function here are the weights and the biases of the neural network. And if you're able to get that, then you have this fixed system that given any new input, you can get a representation of the output. Given this input, you can get this back. And that way it's compressed in the sense of how much data it takes to store it, but you're also able to get this function that can return a new output that hopefully conserves physics. The other technique, the other problem with this typically is there's different types of way of representing simulation data, something called mesh heterogeneity, which is meshes can be on a structured grid, it can be unstructured, it can be completely meshless if you look into isogeometric analysis. So there's a lot of things that you can't necessarily do. A lot of work go from unstructured mesh to structured grid. The good thing about this cleaned up data set is that it's mostly on a structured grid, but this is something that's also important to keep in mind when you're trying to train these sort of implicit functions. So this is the process of what an implicit neural function does. You go from your simulation data, which in this case is the data set that we're working with. You transform them in a way that can be accepted into the architecture, the neural network architecture, which are some of the augmentations we saw from the previous work, but for more specifically the raw data, which I'll be presenting on the next slide. And then you train your function. Which is just inputs output pairs from the raw data, and you store it. That way, after storing it, you're able to query any point at any resolution, and that helps with kind of the problem of having different types of resolutions or different types of mesh representations that we saw in the previous slide. So that is the overall process. In order to get there, though, especially with the setup that this study used, which is the well data. It has different types of simulations for different types of field. There's biological data, there's magnetism, there's physics or fluid flow analysis, fluid viscosity, turbulence modeling. Different simulations have very different setups. So in order to train an implicit neural function, what you would need to do is first extract different types of metadata. So we're moving away from the images to the raw simulation data. The good thing about the well is it stores this in a very structured HD5 file. That's not the case for all simulations, but this is something that we get from this data set. So the process is trying to identify what type of grid are we dealing with? Is this spherical? Is this Cartesian? Is this a 2D or a 3D problem? What resolution of data are we dealing with? So back to that 256 by 256 or the images portion that we saw in this work. We also want to look at the classification of fields. It's not enough to just extract all the data. We need to be able to determine, is this a scalar field? Is this a vector field? If it's a vector field, we want to be able to split that into its component parts so that everything is uniform from the scalar perspective. We also want to be able to split based on, is this a static field or is this a dynamic field? For static fields, you don't necessarily need to encode it so much. So there's this idea of things like density, speed of sounds. Those are constant values, or if they are constant in that simulation, because there are simulations that they can change. If they're constant in that simulation, that's something you can easily encode in a different way that doesn't necessarily need to go through the neural implicit process. But if they are dynamic and they do change in time, if they're time evolving, you want to be able to capture that as well. So like I was talking about, static and dynamic have different types of way to store the data. The way that this work goes about it is when you have a static field, things that don't change with time, density, you take it and just compress it into float 16. So that's a simple 2 times compression. That's something that can be directly stored. For dynamic fields, this is something where a lot of the data is concentrated. there's a lot of data because it varies per time step. That's something you want to get the benefits of neural compression for like 100 times compression. And that's where we go through the neural network architecture, which is SINCPS here, which I'm going to be presenting. Next slide, I believe. And then use the learned weights like we talked about as the storage strategy instead. There are other things that you want to take note of. Again, like I mentioned, machine learning likes data organized, very well distributed in terms of the actual distribution of the data. So there's things like coordinate normalization that helps so that there's not one coordinate that's pulling it from one direction to another. So it just allows for things like stable training. So you can get away with not doing this. It just takes a longer time to be able to get your training to the loss that you want to. And then things like normalization, obviously score normalization goes away from having things have pressure in the order of 100 of thousands of pascals to really small velocities that are meters of seconds to large values like density for 1,000 kilograms per meter squared or cubed. And that's something you want to be able to normalize so that the distribution itself follows a uniform and follows a bell curve or a Gaussian function. So let's say we did all of that. We still have the problem that we don't want it. We have a lot of data. So just to put this in perspective, a 2D simulation with 50 time steps for 256 by 256 image grid, uniform grid, will have like over 3 million coordinate value pairs. So that's a lot of data. And we have larger time steps. We have 3D simulations. This is not something we want the model to overfit with. So there needs to be some sort of augmentations for how you're sampling for each of those different models. So that's done via random sampling in this case, but there's other different ways to do that. And this is the network. It is, like I mentioned, a neural network, a fully connected neural network. The only difference is it has some sort of different ways of encoding. So each of the activation functions from this follow a sinusoidal function to be able to capture different frequencies of the simulation. And there's also Fourier coding associated with things like going from pi to 512 pi to be able to capture different levels of the frequency domain. So that's what's special about this. It's very good for data that's not necessarily follows a uniform or a normal based analysis where there's like pockets of large things going on here, small things going on here, which is the case for simulation-based data. You go from input coordinates of like, in the case of 2D, we have X and Y in the time dimension, and you go all the way to predicting things like density, pressure, velocity, displacement, things like that, depending on the type of simulation that you're focusing on. So like I kind of alluded to, depending on the type of simulation you're focusing on, you can't necessarily train one implicit neural representation for all different types of simulations because different things focus on different aspects. But depending on the class of simulations, you can predict, be able to get different evaluation metrics for it. So just to avoid putting 22 separate things on this slide, kind of classified them by 8 physics domains in general. There are still specific things within these simulations that are very specific to this one simulation that doesn't fall within the others in the class. So this is more from a classification or organization visualization perspective, but each individual neural representation. So these are the individual simulations in this table. All 22 of them have an implicit neural representation. So we have about 32, that's what it ended up being, 38 megabytes of stored weights and biases of the neural network, all 22 of them. So that's what we get for this kind of compression-based analysis. And these are some of the examples of what these classes look like from magnetohydrodynamics to fluid dynamics to astrophysics, and things ended up being better than the other. once you go from the compression space and try to recreate that compression space. But let's look at some of the results based on these classes. Again, the plus and minus is because we have multiple per class. Some only have one, as we saw in the previous slide. So that doesn't have the plus and minus here. But the compressions that we're able to achieve using this sort of implicit neural compression go all the way from over 100 to 25,000 across all these data sets. So we were able to reduce things from like 2 terabytes to 40 megabytes of data. And this is on the aspect or in the same scale as we would see with traditional videos, which have been used in scientific or just in general ML to train good video generation models. If you want to be able to scale up in the terms of data that you need to process and train these models. So the compression is good. That's what we want to see. What we're looking at in this third column is the signal to noise ratio, which is something that's typically reported from these sort of compression or lossless strategies. And anything below 20 or about 20, anything above 30 is very bad. But the range is between 20 and below 20 is necessarily acceptable from a signal to noise ratio. So there are some models that exceed it and some models that are below it, and the astrophysics, which was the model that we saw in the previous slide, is above it. So there are still implementations that we need to try to be able to get the signal to noise ratio smaller, and that could include things of increasing the sampling, the random sampling. So right now it's per batch size, about 50,000 sample points. So that could be easily expanded to be able to allow for more data per batch run because the compute allows for it. And then we have things called spectral error. It's a regular sort of error. So 0 is where we want to be. And right now it's very low across the board. Future work for this includes specifically targeting the specific domain. So for example, fluid dynamics, there could be things that we want to be able to measure the boundary conditions to see if those are being obeyed or if they're being violated. That's something we want to know from a compression perspective. There's also specific metrics within each of those domains. That's something that's important for that domain that you want to be able to ensure that has the least error, the least spectral error. So it's all about trade-offs with lossy compression. You want to preserve the important stuff and you can do less with the less important stuff. So that case by case basis is something that still needs to be done. But in terms of the reconstruction quality, so after training the model and then passing a new input, what do we get from the learned weights and biases? For some models, looking at the errors, they're very low. It's mostly from a resolution perspective. But for some models, like we saw before, they're relatively higher. So the astrophysics that I alluded to before. So it's not by any means perfect. There are still some high error zones within some sort of simulation like fluid dynamics. So there's some things to improve and fix upon and build on. But what's really good about this model, like I mentioned before, is the amount of time it takes to train these models. So for acoustic scattering over those 50,000 steps, it took only about 2 hours to train using the Cerebras chip. So that's something that you can easily iterate on, train again within a couple of hours, iterate on, train again within a couple of hours to be able to get the kind of signal to noise ratio, the metrics that you're tracking for each of those simulations set below a certain threshold. So that's something that I think is the benefit of this method. And if you can get this method where get like 38 megabytes worth of data stored within these terabytes worth of simulation, which allows for that back to the scientific ML that we were talking about. So I've kind of presented today the two paradigms. There's other different things you can do. A lot of people are working on different things, but I think there's always going to be a challenge when it comes to getting data that's tractable in a way that can be used for training machine learning models. So someone has to solve that problem. Different ways of solving things, focusing on using reduced representation, using implicit data, finding a way to combine these two in some sort of a hybrid approach. It's a lot of really cool things that you can do from improvements for future work. But yeah, I kind of left a bunch of time for questions. So that is the presentation. Obviously, a lot of this, the work out of ByteBoost and the work following was out of a specific grant that I got through Access to be able to run it through the CS3 chip via Neocortex through the PSC. But I am happy to take any questions.
Thank you, Jessica. That is a really nice talk and really great use of Neocortex. So please, for those of you in attendance, feel free to write your questions in the chat or raise your hand or unmute your microphone to present your questions to Jessica.
I would have a question. Jessica, can you say a few words about like how you used actually the CS3 and like what your experience was about that, just briefly, and then
Yeah, definitely. So the CS3 has a really good resource via their model zoo that has a bunch of templates for standard architectures, so like transformers, in this case, vision transformers, was already well represented there. So it's mostly just tweaking kind of the inputs to be able to allow it to process the data that I was bringing into it. And then obviously the way that the data was being extracted to be able to predict stuff. So that was the tweaking from the transformer. But for the implicit neural compression, that required a little bit more work because that's a little non-traditional type of architecture. But I thought there's still some baseline starting point, like the fully connected neural network is already there. You just need to be able to modify things like the activation functions. The kind of Fourier embedding that I talked about is a new kind of module block that you need to run and then plug it into the model zoo and kind of link up where that's supposed to be, where that goes. And if you go through the network tree or the tree of files associated with that, it's just linking where to find that information. But after doing that, it works relatively straightforward.
thank you.
Thank you, Jessica. So another question that I have is, what comes next, right? So, and what is your anticipated like need for compute, and if that can be, if you're planning to use the wafer-scale engine?
Yeah. So these were really good test full experiments to be able to see if this is possible. A lot of them were still on reduced representation, still large, but you can go larger with the amount of simulation data that's out there. So there's this field of engineering design called extreme design. There are situations where it requires a lot of data to process. It requires a lot of compute to process. There are things that are not traditionally solved for. So think of like Mars missions. Like that's not something that's traditionally accounted for within engineering design. So that is kind of the field that I'm focusing on next. And the thing with this field is a lot of the simulations that I mentioned that come out of these fields are really large data. So this kind of work that I presented, the last compression, is a means to an end. So the end being the scientific ML pipeline to be able to discover new data or to be able to understand what's going on within the simulation data. So I think that's kind of the next step, to be able to apply this to specific extreme fields that have larger simulation data set, less structured, that require more work. But this was a really good proof of concept that this would work if you were able to get your data organized and you can represent it on the CS3 and get significant speed up. Even if the speed up was, this case, like 6x, it's like pretty good for like something that has so much large data that will traditionally take months to
Hello, Jessica.
Hi.
Yes, your presentation is quite interesting. I just want to, I wonder, I came late 30 minutes late to see your presentation, but I like the way that you, com- I mean, what I saw is very interesting. I
Thank
would like
you.
to know if your data must be structured, right? No,
Mhm.
okay, you cannot, we cannot, okay, your presentation
Yeah,
is with the structured
it's
data. What about
it's
non-structural data? I mean,
yeah, that's a good point. I think that's a while ago. Like I mentioned previously, it's a good point that you brought up. There's a problem with the type of data structure that you have.
uh-huh.
Right now, I focused only on the structured grid. So having uniform connectivity, regular spacing sort of data, which is well behaved. But there are different types of data that don't necessarily follow that pattern. So a lot of the engineering simulation fluid dynamics work largely works on unstructured meshes. So that's the future work that I was talking about, moving forward with unstructured meshes as a type of data part. I think right now, a lot of paradigms within unstructured meshes goes from an unstructured mesh and then they convert it into a structured grid via some sort of mapping process or using things like adjacency matrix to be able to position and align everything in a structured grid. If you're going away from unstructured meshes to meshless or particles, that's even more difficult.
Yes. Yeah.
But yeah, so it's a huge question that's still an open question within the simulation space right now for scientific ML processes. And I think it's something that needs to be addressed.
Okay. Thank you very much.
Yeah.
Thank you, Humberto, for the question, Jessica, for the answer. We have another question in the chat from Pratyush. Do you want to maybe unmute yourself, Pratyush, or do you prefer that I present the question?
I can also read it.
Okay, I'll read it out loud. So we have the question in the recording. So it says, how does this differ from existing approaches like representation learning, clustering plus PCA in ML, etc.?
Yeah.
For example,
Yeah,
extracting key
that's
features from our datasets with and without compression.
Yeah, that's a really good question. So existing approaches, this is, I wouldn't say it differs, it's an application of representational learning. So not clustering or PCA, but from like trying to compress. The second type of work is compression-based analysis. So that goes into kind of the width compression point that you brought up. But the first work was a different types of paradigm. It's more of a vision transformer, if you're aware of that, where it uses, not in the case of CNN that uses convolutions, but attention-based mechanisms where you're able to attend to different parts of the image based on specialized weighting that weights important parts of the image more than other parts of the image. It's a traditional attention-based mechanism. So that's what the first work was doing. It was learning key features via the attention mechanisms in the traditional transformer or vision transformer architecture. So it is still a way of extracting key features. It's just what type of way are you using. Clustering for the first work is what you would traditionally have done without vision transformers. So you would do something like k-means and you would use that to be able to classify what type of simulation you're using. But if you want to do something like the other task that we evaluated on, which was the next time step prediction, which is given an image t equals 0, can you predict what t equals 1 would be? That's something that moves away from traditional clustering and actually has to have an understanding of the temporal component of that data. And there are some kind of temporal based analysis that do research in that field. So this is not necessarily suggesting a new architecture. It's more taking existing architectures and applying them to physics simulation data, but taking care to also notice the differences in how we process the physics data, which I think is where a lot of this work spends a lot of time in.
Thank you, Jessica. Pratish, hope that answers the question. If you have any follow-up question to Jessica, let us know.
You're welcome.
Says yes. Thanks. So another question: how do you see physics-aware AI models like PhySiViT and SINCPS evolving over the next 3-5 years? And what's the role of, or what role could platforms like Neocortex and other AI testbeds that are out there play in enabling those capabilities?
Yeah, that's a really good question. I think that's where a lot of the research is moving towards, like physics aware models. There's the problem with physics, unlike chemistry or biology, it's pretty hard to define. The physics means a lot of different things for different people, and so once you solve the problem of what kind of physics are we trying to solve, then you get into really interesting pockets of simulation. The work that I'm focusing on within engineering design lives in two types of paradigms. Like, for example, very common simulation is fluid structure analysis or interaction, where you have a design like a car and you're passing it over fluid flow like air, and you're able to optimize the car design for things like drag go around to make it more streamlined. A physics-aware model can do away with a lot of the bottlenecks with simulation, which largely has to do with the time to run simulations and the efficiency or the accuracy of those simulations. If anything, there's a trade-off in simulation. So the finer the mesh, the longer the time, the more accurate. But if you want it faster, it's less accurate. So I'm thinking the way the field is going is a fundamental or foundation physics AI model, kind of how we have with coding or text-based LLM models, where you're able to get a lot of that forward. A lot of people have already done a lot of the forward effort to training this fundamental AI model or physics model, and you're now able to fine-tune it for a specific case or use case studies. Where I think Cerebras or any other architecture that's really good at speeding up things that have uses a different paradigm, so things like GPUs, is in order to build such systems, you either need to go through the process of traditional input-output pairs training, which runs into the bottleneck of data like I presented here. Or if you can get the simulation evaluation fast enough, you can actually incorporate it within the loop where you don't need all the data. First, we have these inputs, we pass it to the simulation engine, it runs the simulation, it returns the output, you return the process, do the back propagation, and then go back, return, repeat this process. So that way you can train for longer. The only bottleneck in this system right now is the simulations take a while, which is why really good people like the Well have created these large data sets and spent a lot of time doing that for us. But if you can get it fast enough that you can put it in a loop, this solves a lot of problems, and you can train and build out bigger and more accurate data set for more specific things. So I think a lot of the compute should go towards optimizing things that are not GPU inherent, but like simulation based inherent. So a lot of simulations still require a lot of CPU, not just GPU, especially if you move into some of the fluid structure interaction. So I think there's a different kind of architecture paradigm that needs to shift from just GPU-based analysis in order to allow for these faster simulation times.
Thank you, Jessica. That's very, very interesting. And certainly, yeah, I see that being very transformative to many fields. But that's pretty cool what you just shared. Okay, so I see we have 2 minutes left. I think anyone has, maybe we have time for one final question from the audience. If we don't have questions, then I would like to thank Jessica again for her great presentation. And with that, remind everyone that we are having monthly webinars, right, where we have researchers who have familiarity with the wafer-scale engine, either through Neocortex or other deployments. And our goal is to just help researchers, the research community, get inspired by the great achievements and results that have been produced by some of our researchers. So I see in the audience we have also Matthew Moreno, who presented last time, and his recording, the recording of his talk is available in the Neocortex website, and same with Jessica's. We'll have the recording and slides available in the Neocortex webpage. With the last few seconds that I have left, I would like to also invite everybody to consider applying for ByBoost, the cyber training program where you will be looking at different AI accelerators, not only the wafer-scale engine, but there are also graph-core IPUs, AMD GPUs, also some of the fastest NVIDIA GPUs. And the mission and vision of this program is to teach researchers how to select among these different options, and then also engage directly with experts in the technologies and deploy their own research and code. So as Jessica shared, that she participated in the 2025 cohort, and that helped with some of the work that she presented today. So with that, thank you again, Jessica, for a great presentation. And thank you everybody who joined this seminar. Have a good rest of your day. Bye-bye.
Bye.